So welcome. Is your phone owned? Perhaps you want to take your battery out, if anyone's worried. Just kidding. My name is John Herring. I'm here with Kevin Mahaffey and Anthony Lineberry. We're from Flexilis. We focus exclusively on mobile security research and software development. For the past couple of years, we've been working on mobile devices. It's interesting, we were kind of musing at the evolution of mobile devices. We spoke at DEF CON a few years back. In 2004, the Razor was the coolest device. It had Bluetooth. There were some problems with similar devices. Just a few years later, we're already seeing these devices essentially becoming PCs, and we're going to talk about the host of issues that come with the evolution of these devices. So the first thing we want to talk about is a real-world attack scenario. I'm sure you're all interested in exactly what could happen. We actually have a demo in place, but unfortunately I can't tell if it's that we have 25 phones up here or we're in the bowels of the room, but the cell phone reception is not good, so we'll just show you on the slides. Essentially, WAP over SMS is something that is the center of one of the demos or the exploits we're going to be talking about. WAP is a wireless application protocol. It's open international standard. Basically, it's something that layers over SMS, and WAP push specifically is incorporated into the specification that allows content to be pushed for mobile handset without user intervention. So this is something that was built for good intentions. You can deliver ringtones, advertisements that are opt-in. There's lots of things that are meant to be done with this technology, but one of the issues that we found is that in certain circumstances, it's possible to actually leverage this technology as an end user without any authentication. So you can see the WAP protocol, the protocol stack. What's most interesting to us here is the wireless datagram protocol, which is what WAP is layered on. So Kevin, maybe you can walk us through exactly the attack and how this works.
So, absolutely. So under normal circumstances, WAP has a very, very, very complex architecture, and this is probably the simplest WAP diagram you'll ever see. Really, the WAP can be sent over all sorts of different data bearers, USSD if you're familiar with that, SMS, both GSM and CDMA, and they are entirely different. Under normal circumstances, what you have is an SMSC, which is kind of like a routing system for the carriers to send SMSs between phones. And under normal circumstances, the SMSC has a push proxy gateway that's associated with it. And the phone has in its configuration a SMS number that it trusts as an authenticated gateway. And under normal circumstances, all WAP push services are registered with the carrier that go through the registered push proxy gateway, and everyone's happy. So under a bad situation, if the device does not respect the configuration setting to only trust WAP push messages from a specific source, then we have all sorts of problems. Any device on the network can send something through the SMSC, and if the SMSC forwards it to the terminating device, then that device will accept it just as if it came from the trusted push proxy gateway. And so this is an attack we unfortunately can't demo right now, but it's been in the wild since 2008. It's fairly interesting. There are a whole bunch of OEMs that have shipped with misconfigured security policies, specifically in Windows Mobile. And we've seen this on Samsung, HTC, Pantech, Motorola, you name it. And it's kind of interesting that they all had the exact same misconfiguration, and I have no idea how that sort of thing could be that prevalent.
And so just to be clear, the result of this attack is essentially there's no user intervention. Your device is sitting there. Someone can force an arbitrary URL to open. So I could force a web browser, Pocket IE or Opera, on your mobile device just to open arbitrarily. That could be coupled with a browser exploit, or you could have it point to an arbitrary URL with an actual file, so you could force it to load software. And if you're not looking at your phone or if it's sitting in your pocket, this happens completely unbeknownst to you without user intervention. Another thing to be clear about is that this is taking place in the wild, but the operators have systems in place that they're absolutely able to understand when this type of traffic is taking place. So they're monitoring this, and it's something that's actively being worked on at all levels to be fixed. This is not a Microsoft issue, really. It's an OEM issue. Microsoft actually has set the policies in a way that's the right way to be set, and then at some point in the chain when these devices are shipped, they get misconfigured. So at the OEM level, that's where the problem has primarily been, and we're working to hopefully help solve this problem the best we can. We've actually created a hotfix tool for anyone with a device that you're worried might be vulnerable. You can go ahead and download the hotfix tool. It'll scan, detect if the device is vulnerable for 4 specific issues, and hotfix the device until an actual patch is able to be pushed out to deal with this issue. I definitely recommend you do that. If you're an IT admin and you have an enterprise with the deployment of Windows mobile devices, it probably makes sense to make sure that you're good to go on this. And I also would just let you know that there are certain instances, especially with overseas carriers, that certain functionality might not continue to operate when you put this patch on. So it's kind of it's complex. It'll keep you safe from these types of attacks, but in certain cases, like, you might not be able to get ringtone delivery through the carriers. So just be aware of that. So that's an example of a real-world attack. Let's talk about the environment around mobile security, give you an idea of what's going on in the world today relative to these devices. So I'm sure we all know this, mobile devices are absolutely PCs today, and most of the functionality is extremely similar to what people are doing on their desktops. So browsing the web, sending email, accessing social networks, downloading applications. Just in the past 24 months, things have changed pretty considerably. And it's a great thing and not such a great thing, the speed at which these are evolving. So there's this arms race of creating really amazing new devices with cool, innovative user interfaces and applications and faster high-speed networks. And that's causing each of the manufacturers to create better and better devices. But at the same time, as they're evolving very quickly, we're starting to see a set of technology that is introducing many of the problems that we've seen on the PC side of things. And our hope is that we can take a lot of the learnings we've had over the last 10 years and apply that to mobile security. The key factors driving the threats, device advancement, absolutely. We talked about in 2004, not that long ago, the Motorola Razr was one of the coolest devices out there because it was thin. You look at the iPhone now, it's almost incomparable, and that's only 4.5 years later, 5 years later. So that is a key factor driving the threats. Third-party application adoption also. We saw this on the PC as in the late 90s, the shareware movement and applications started to really get downloaded through the internet. We started to see malware, spyware, other types of malicious entities piggyback onto software itself. And then finally, persistent connections. So the same things that enabled worms, and that when you had your cable modem or your DSL connection constantly connected to the internet, we're going to see a lot of the same issues having persistent connections to mobile devices, and it's something that we need to be aware of. Mobile data usage is absolutely spiking, and I believe in 3 years from now, we will hit the same amount of actual broadband usage that we're using on desktop PCs today. So you can imagine the amount of throughput. It's going to be unbelievable, the data that's flowing through mobile networks.
One thing that's interesting to note is that unlike PCs, mobiles need push services to operate. For example, an SMS. Right now that's operated, a carrier sends an SMS directly to your phone. It's not like an email protocol where you have a persistent connection to a server or something where it's some sort of polling architecture. Phone calls, things like that, firewalling is not the answer. You can't just hide behind some network address translation and your phone's going to be safe.
So we understand what's driving the threats. What are the incentives for attackers? Attackers are generally pretty lazy when it comes down to it. They're going to go for the lowest hanging fruit and the easiest attack. Right now that's on the desktop, but it's changing pretty quickly. For a while, everyone's talked about attacks against mobile devices, but I think that now it's finally becoming a reality as we're starting to see actual penetration of usage of these devices come to the mainstream. I mean, just look around everywhere you go. Everybody's got a smart device, and that's changing more and more every day. What's really different about mobile devices is the way by which the bounty of the attack, if you will. So how do you monetize an attack? As an attacker on the desktop, you can take control of the device and make it part of a botnet for spam. You can steal people's personal information, credit card numbers, and things like that, and use that to monetize. There's a few ways, but there's not really a way of direct monetization. On the mobile side of things, totally different. These things are virtual wallets. So reverse SMS billing, there's all sorts of different payment mechanisms tied directly to your cell phone bill. send a packet, money goes flying. This is absolutely unique to mobile and something that I'm sure will be driving more and more threats. There's been very light examples of this in Russia. There was an attack against devices where a piece of malware would hold your device hostage until you clicked this pop-up dialog box that would then send the equivalent of $7 to an offshore account.
I can't underscore enough how important this is. I mean, never in the history of the internet has a normal person been able to send a single packet and money goes flying around. Just think about that for a second. Like UDP packet somewhere and just dollar goes out of your account. That's, if you look at where attacks are going, attackers need to be incentivized. And if a single packet money transfer mechanism isn't an incentive, I don't know what is.
So I'd say for the end user, that's more of a concern. For IT admins, enterprise users, I'd say network resources are going to be one of the biggest risks. So direct attacks against a corporate enterprise, for example, corporate espionage or just a broad attack. These devices are accessing privileged network resources. You can spend a lot of time and money securing your network perimeter. But if a mobile device gets compromised, which then has trusted access inside the firewall of that corporate network, then that's not good. And I'm guessing that that's going to be happening more and more. So understanding that you need to try and be as cognizant of security of your mobile devices as you do your actual network perimeter and your desktop endpoints, that's something that if we don't pay attention to that, the mobile device will be the soft point to the juicy core. And then finally, valuable data. This is somewhat similar to desktops in that there is sensitive personal and corporate data on a PC and on a mobile device. But one of the different things is there's actually a lot more data. A lot can be learned about you, your social graph, as we might call it. So if you did an analysis of all the people you're texting and calling, you can look at who you're interacting with and learn a lot about a person. There's a lot of personal information there. You can look at their logs of all their communications. Location is becoming a bigger and bigger issue, so privacy as it relates to security. Mobile devices, in my opinion, are the most personal computer, and people are identifying with them more and more every day. It's kind of an extension of yourself. So as sensitive as your desktop is, I think that the mobile device is even more sensitive, and that's going to be driving incentives for attackers to start coming after these. So this is a really hard problem to solve. Mobile, there's no one silver bullet, and one of the hardest parts is that mobile is mobile. So it's a constrained defensive environment. We have battery life, processing power. There's a whole host of limitations, and dealing with the trade-off of performance versus security is something that's going to be a constant battle moving forward for everybody involved with security, from software developers to the OEMs and operators across the board. That's going to be something that we have to deal with. And security is constrained, so in defending these devices, we're constrained, but the attackers aren't. So the attackers are only getting more and more advanced, but our defenses are only getting constrained in some ways, and the devices the power is increasing, but at the same time, there's just lots of limitations put in place. So I would say that the attacks, if we aren't cognizant of being on top of security, could outpace the defenses. Responding to the threats is really challenging. This is a big problem we'll talk a little bit more about. It's not just as easy as saying, oh, there's a zero-day exploit, let's issue a patch, push it out there, everyone's good to go. I can absolutely empathize with everyone in the value chain of mobile technology. It's a very challenging problem, and everyone's working super hard to keep end users safe. Mobile devices, they're fragmented yet consistent. So you'll hear the argument, well, there's so many different operating systems, especially smart platforms, so Windows Mobile, Symbian, BlackBerry, Android, iPhone, now the Palm Pre. One attack, unlike Windows, which is a more monoculture environment, can't apply to all these. Yes, I understand that argument, but at the same time, although it's fragmented, it's actually in some ways more consistent. So look at the iPhone. I think there's 17 million iPhones today. The iPhone is the iPhone. Generally, they're the same. So one exploit for the iPhone is going to work across 17 million devices, growing at an incredibly rapid pace. And if you look at desktop computers or desktop PCs, they may have different ports running, different applications. There's lots of different configurations. That's really not the case on mobile devices. They're pretty consistent in a lot of ways once you get down to that OS level. So it's interesting when you think about, yes, it's fragmented, but at the same time, it's consistent. And I mean, there's a few other great talks today on mobile about SMS-based attacks, and you look at how these attacks and their consistency enable them to apply to a lot of other devices. So the real elephant under the rug is based on the fragmentation across these devices. So it's fragmented from an update standpoint, but less fragmented from an attack standpoint. So what I mean by this is, let's say you have a device of a certain operating system, and it's on 130 carriers worldwide, typical scenario. If there's a vulnerability that requires a firmware update, every single carrier that supports that is going to want to qualify that to make sure when it comes onto their network, it isn't crashing the devices, not causing service call instances. It becomes a very, very difficult challenge. So it's not just as easy as pushing out a patch. And because of that, I think the security community really needs to focus on understanding the unique nuances of mobile and making sure that we work with everybody in a way that takes this into account. A lot of the issues that we've found, we try and make sure that we give a really reasonable amount of lead time in trying to deal with these issues and be as flexible as possible, just because it's not that easy. And at the end of the day, this isn't about disclosing vulnerabilities, it's about keeping people safe by means of disclosing vulnerabilities. The end users are really what matter. And so as long as we maintain that focus, I think we'll be okay, but it's a big challenge.
From an update cycle standpoint, 4 months is wonderful in mobile. I mean, I can't think of an instance where 4 months is wonderful in a desktop piece of software. But given the complexity of the update situation, it's funny how long these cycles need to be to actually get a patch out.
So we'll talk about it a little bit more. Great example with this fuzzing technology we're about to talk about. We found a 0-day in the iPhone and Bluetooth that took advantage of a vulnerability that enabled us remote code execution. Apple and AT&T were great. They moved really quickly. I think it was about 3.5 or 4 months from the day we talked to them to actually getting it patched in the field, and it was in the 1.1 update. That was a pretty ideal example of being able to respond to a threat. But that just gives you an idea of how fast one might or might not be able to respond to these threats. And it's just, again, one of the unique challenges of mobile that's going to make things very difficult moving forward. So the mobile patch process, like we talked about, manufacturers have to customize for firmware. Often manufacturers want to run their own QA. One other unique nuance, if you touch radio code, often the regulatory body that governs the radio code of your country needs to make sure that checks out. So FCC in this case in our country, and then carrier qualifications. So there's all these different checks that have to go through. It's not just the desktop environment where Microsoft, there's a problem, they get on top of it, they patch it, they push an out-of-band patch, if you will. That's awesome, and we don't get to have that awesomeness on the mobile space. So,
one thing that's interesting to note, if you think about how many carriers customize the firmwares for their phones, let's take the Motorola Q, for example. Even a few years ago, they had 133 different carrier-specific customizations. So let's imagine Motorola develops this phone, gets it out to all these carriers, and all these people have the phones in the wild. Then, some intrepid security researcher comes around and says, "Hey, I found a vulnerability. You guys can fix this in 6 weeks, right?" And they say, "Ha ha ha." And they patch it on each one of these 133 branches, and then they have to go through 133 internal QA cycles, and anyone who deals with QA in the mobile space knows how long that takes. Then if they're on a single chip radio solution, they'll have to hit the FCC, and then each one of those carriers will have to do a carrier qual, which can take 0 to n weeks. So you can quickly imagine how a single vulnerability can cost millions and millions of dollars. And we say this 133 times 133 times 133, 4 months is freaking smoking.
So we talked a little bit about the environment. Let's talk about how we discover vulnerabilities, the type of research we're doing to audit these devices, make sure that they're safe, do our best to keep everybody safe as they use them.
So auditing code on mobile devices, it's really not that much different than auditing for desktop software. You're going to hit the code first and do a lot of low-hanging fruit, look for stir copies, sprintf, double freeze, etc. Look for a lot of pointer manipulation. And there's a lot of tools out there too that enable you to do this kind of stuff. IDA has support for, I believe, for at least for ARM. I think for the iPhone.
Yeah.
Okay. And then also calls for execution of exec VE system with user supplied arguments, and this is stuff that we've obviously all known for the past 10 years or so, but in the mobile world they've never really had to worry about security before, so they never put a lot of thought into making these insecure calls.
And I think it's important to note, imagine yourself, I bet most of the people here have a background working with internet protocols. Imagine that you have your background in a telecom protocol system. Maybe you've been on SS7 networks before. Nobody has access to those, so you don't need to do validation. I mean, the most you've had to do before is do interrupt testing, right? If you pass through interrupt testing, you ship the product, you're good to go. And so now imagine that you're the same person developing software for a mobile device using your same development practices, and now this mobile device is on the internet. So your coding standard that was just peachy on a mobile network is now ridiculously vulnerable because you're accepting packets from, God knows who.
One other thing I would add is that really I think in the past 2 years, 18 months, this has changed. There are so many more developers developing applications for mobile devices, and lots of these people are first-time developers, especially with the iPhone and Android. They've got an awesome developer community, and tons of users are developing apps for themselves. They are not necessarily cognizant of secure code or secure coding practices, and that could cause a problem moving forward. And we'll talk more about this, but the idea of new developers building applications on a platform that could introduce problems to the entire devices themselves is something that we find very interesting.
Another thing that is a good way for auditing this stuff is really no different than the desktop in the case of using third-party libraries. There's always the problem of a vulnerability being discovered in some third-party lib, and any software that's implementing that will usually by default be vulnerable to that. We've had problems with that in Android and iPhone. I know some of the very first Android vulnerabilities were found were Alfredo Ortega's, I think it was in libbmp and some PNG stuff, back when it was just an SDK release before any actual hardware was released. The iPhone, they had problems with libtiff like a year or so ago. And a lot of these problems, you can just look in the change sets for these third-party libraries because it's...
grep for security.
Yeah. and it goes kind of back to the patching problem where it's a lot more difficult for them to keep their libraries in sync. I believe Android alone is using like over 70 third-party libraries in their source code. And so it's kind of a problem with that, keeping it together.
And given the update cycle, let's imagine there's an ODay in one of these libraries. Even if we did go as fast as we possibly could, there's still that 4-month gap between the time when the new library gets committed to the source tree and new firmware update gets put on your phone, assuming you actually put it on your phone.
So one other non-traditional way we found vulnerabilities, believe it or not, we have found issues through Twitter. Security researchers talking about the type of research that we're doing. We've actually looked at something that they're mentioning and been able to reverse engineer the research that they're doing and find vulnerabilities actually faster and other research vulnerabilities around what they were looking at. So the faster information's disseminating and more publicly, it's just very interesting watching how people are leveraging this knowledge and collective knowledge to detect vulnerabilities. So there's obviously the stuff that starts with looking at the code, looking at third-party libraries, and then there's also some pretty non-traditional ways, and this will apply to anything, but just relative to mobile, we found this really interesting. We found a couple bugs via this methodology.
And if you're responsible for mobile security, personally for your family or business, Twitter's a great way. Just keep a safe search on TweetDeck or something like that, search for mobile security, and you'll have some nice entertainment.
So let's talk about actually auditing the mobile devices. There's a tool we've developed. It's called Fuzzit. It's a mobile fuzzing framework. Talk about some software and hardware related to it, and we're going to be releasing this at some point in the very near future.
So for those of you who aren't familiar, all three of you who don't know what a fuzzer is, it's basically a way to automatically inject data into a system, and typically this is unexpected, out-of-band, or otherwise malformed data. You can also do this in terms of fuzzing malformed data structures and state. So sending a good data structure in a bad state is also fuzzing. And so we went out and designed a new fuzzing tool for mobile for various reasons, specifically because there are some problems that make mobile fuzzing very difficult for existing tools. We also wanted to do something that covers the gamut of things necessary for a good fuzzing tool. For example, a fuzzer a lot of times is just a generator, something that can throw a whole bunch of data at something. The simplest example is pipe dev ran to your favorite, command line executable. The other things we wanted to handle are the injection. Injection on mobile devices is very difficult because you either have to pipe data into the device directly, like with software on that device, or through some sort of radio interface. So it's certainly not simple. Also, with a lot of mobile protocols, they're very stateful. Bluetooth is an excellent example of this. And the last thing is result analysis. Not everything will just result in a crash. Sometimes you need to say, hey, what happened to this radio state? What code did it give me back? So all these things are important. The big things we wanted to do is produce something that somebody out of the box can audit mobile phones. So our goal is to have this be used by manufacturers, carriers, anyone who is responsible for securing mobile devices. And a slight tangent, has anyone here heard of GitHub? Yeah. Yes. So, okay, here's a scenario. Somebody presents a wonderful security tool at Black Hat. How often does it get updated? Answer, never. Almost never. So our goal is not to have a tool that you say, wow, that's a great tool. Well, hopefully you say that's a great tool. But we actually want this to be used. I mean, our goal in developing this is to actually help carriers, manufacturers, and everybody build more secure devices. So this tool is going to be available on GitHub, and what that means is that anyone can fork it, they can make additions, and they can submit it back. And so this encourages everyone to add new test cases, new fuzzers, and eventually we'll build a corpus of testing systems so that we can really have a robust auditing suite that, I hope at some point becomes the standard for security testing. So none of these silly little low-hanging fruit bugs will ever get out again, because honestly, some of the audits we've seen, it's kind of sad. The bugs just, 10 test cases in, it just, hoses the phone. So why something new? We addressed this slightly. State of mobile auditing is primitive. You can imagine it's really difficult to interact with these things. Mobile devices have a lot of unique constraints in the protocols they use, and we also have some techniques we've developed over the years that we wanted to introduce, so this might make a decent general purpose fuzzer as well. So the very first thing to note is that the fuzzer is written in Ruby, and the first thing we wanted to do is have a really good domain-specific language, which is basically a language that isn't exactly like the programming language you're used to, but it reads so that basically anyone can understand what's happening. And the framework is built so that a user can define a protocol structure, and then all of the magic happens behind the scenes. So all of the injection, all of the state transition, and whatnot. And so here's a very simple example of defining a packet called packet. It is a type length value protocol. And you can see that it's fairly simple. It's built with intelligent defaults. It has values that are symbolic. So for example, if you're generating something or you're parsing something with this, it will actually tell you what they are in symbolic, not just say 1, 2, 3. The main problem that we have with mobile devices is that we can't just cover TCP/IP. I don't know how many fuzzers you've seen that in the core fuzzing code, they have IP logic in there. And so that just, you have to untangle all sorts of things to actually do something on Bluetooth or something that's not over TCP/IP. And so, what we're talking with mobile protocols, we have SMS, Wi-Fi, NFC, all sorts of stuff. In addition, we also want to cover TCP/IP and file formats, special case of a protocol. The solution we've had is to build a very, very loosely coupled architecture so that you have all of these fuzzing components that are basically interchangeable, so that if you want to rewrite one portion of it for one crazy phone that does something silly, you can do that. It makes it really easy. So a very initial discussion on what the fuzzer does is, you saw this before, is blocks and elements. So a block is like most other fuzzers, a set of data that has multiple elements in it. The elements themselves can be fuzzed. So for example, int has intelligent defaults that will say, hey, this integer will fuzz all of these values that you think it should fuzz, 00, FF, 7F, 80, etc. The next thing that's important to note is that once you have these protocol elements, they don't really do anything in isolation. You can say, hey, I described the HTTP protocol. That doesn't really help. And so the next thing that the system does is it connects it in a tree to all of the protocols. And so when you develop a protocol such as this one, you add it to a global protocol registry. It has a name so that you can reference it later. The interesting thing to note is that if we're trying to make a very, very loosely coupled system, let's say we have a entry for Bluetooth L2 cap, there's umpteen different protocols that can sit on top of that, RFCOM, SDP, etc. We can't have L2 cap know about those protocols because otherwise we have a dependency relationship that's kind of icky. So the fuzzer basically has an abstract data type that allows protocols to kind of mush together when you define these dynamically. And so this is what a fuzzer would look like from the command line. One of the cool things we wanted to do is make it so that fuzzers can be built on the fly. You say, hey, here's a host. I want to attack these protocols, and everything kind of happens. You can see right now we have OGG, L2CAP, GSM, SMS. Anyone can add a protocol into the global registry, and the idea is that the protocols know how to stack together, and so everything will be just peachy. Another major problem with fuzzing mobiles is that you can't just do this on an emulator or simulator. A lot of times you need physical access to hardware. We found that one vulnerability that maybe has some sort of race condition constraint will perform differently on one device or another. So it's really important to actually touch physical hardware. Also, if you look at a lot of physical devices in the wild, they have like 70 pieces of software from different ISVs. So one phone will be different from another phone, and we've seen specifically Bluetooth drivers responsible for this. MMS is sometimes customized by the OEM. So fuzzing one device is not going to be the same as fuzzing another device. And so the next step, so we talked about the generation system, the next step is the injection system. So in the injection system, we wanted to have pre-built injectors so that you don't have to worry about how to get things on an iPhone or an Android. All you say is, I want to fuzz OGG on an Android, and it knows how to do that. Or I want to fuzz OGG on an iPhone, and it'll know how to do that. GSM, same sort of thing. We want to fuzz GSM GSM SMS on Winmo. It'll inject that, and it'll do all sorts of mojo to get that into Winmo. You want to do it on iPhone. All it is a command line parameter. And so let's imagine you saw that big, giant, hairy stack of WAP before. Let's imagine you wanted to fuzz a new WAP protocol that your company is developing for one reason or another. You can basically just implement that one little tiny piece of functionality, and on the command line just stack everything else, and it will fuzz everything just nicely. And so in order to make the injectors common, we defined a protocol that basically allows the fuzzing host to communicate with the injector. And so what this means is that you can inject all sorts of different types of data types into one host, and it uses the same piece of software. So basically you run a piece of software on an iPhone or an Android device, and it just has an open server, and the fuzzing host can connect to it. And there's the other type of injector that we have, which is a host side, which is to say the laptop side, that allows it to communicate with a radio protocol. For example, Wi-Fi or Bluetooth. You don't have anything on the host for that, but we have a special set of injection criteria where we need to throw the radio into raw mode. We need to do all sorts of reconnection logic, and we want to abstract away the protocols from that. So let's imagine you wanted to fuzz some new Bluetooth protocol. You don't want to rewrite all of the connection handling logic, and trust me, it's really, really, really hairy to get a robust fuzzer that you can run 870,000 test cases on without having to reboot it every time. So we've designed it so that once you have these baseline injectors, everyone's life is really, really easy. And so the fuzzer protocol is quite simple. Basically, the host sends a type, length, and a value to the device, and the device will perform some sort of injection. SMS is one of these. Audio, for example, Android, it'll start the media player, play the OGG, and then get the result back. Now, right now, they're fairly simple as did it crash or not, but it's fairly trivial to instrument this with a device-specific debugger so that you can actually get really, really good data back to the host. Imagine if you didn't have this sort of thing, you're really primitive. I mean, I've seen some fuzzing implementations where literally it was a SD card and like an actuator, a little servo that pushed a button on the phone and did it every time, and had a little camera that just kind of recorded it. And so hopefully this will make sure that nobody ever has to do that again.
So one of the examples that for our fuzzing server, or the host that goes on the phone for the injectors, was our iPhone Comm Center fuzzer. And fuzzing SMS, especially on iPhone, seems to be a pretty popular topic this year. So this was our implementation of it, which, talking to Colin Mulliner, seemed to be pretty similar to theirs. We're basically using a dynamic library to intercept reads, writes, and opens and select on the SPI basebands specifically baseband 2, 3, and 4, which are used in incoming SMSs. And our kind of approach to this was we had some name pipes. So we have a standalone binary that runs as a daemon, where the fuzzer is sending PDUs at this. And that standalone daemon takes those and puts them into a name pipe. And then within the hooks, in the select hook, we actually intercept that, and we're sticking a file descriptor from the name pipe into the FD set along with all the baseband devices. And then when a fuzz PDU comes in, select will unblock. We'll see if our name pipe was set in that set, and then we'll actually flip the bit to tell comm center that there's actually data to read from the baseband. Once we intercept that read, we can look and say, okay, are we the ones that told it that there was data to read from the baseband? And then from there, we can actually just go and read from our name pipe and return that into the read buffer as though that came off the baseband. And then we also intercept writes to baseband 4, which is what it uses for checking if it actually did get an SMS. It sends a CNMA, and under normal circumstances, that would return a CMS error from the baseband, but we kind of swallow that and say, yes, we actually did write it, but without actually doing it. And then we reply back with a OK. And we use a simple state machine to keep track of which baseband it's supposed to be reading or writing to. And then we just run that all in there. One of the nice side effects of using this method is that all these hooks on all these basebands we can actually use to monitor activity on each baseband and see all the GSM AT commands coming in, which we can just use for analysis in other situations as well.
The really, really nice thing about the way this device-side fuzzing injector works is that I can be sitting on my laptop from the command line. I can design a new SMS PDU, and it connects to the device and sends it and injects it in the device. I don't have to redeploy anything to device. I can change the PDU. I can add a new protocol. The device just has a little server running, and it sits there. So it makes fuzzing really easy.
And this is just another example. Our goal is to create tools to help keep these devices safer. If you can spend more time on the actual testing part than the implementation part, which is hugely painful, we're trying to abstract away a lot of that complexity and focus on actually securing these devices. So let's look at a demo. This is my favorite part. That doesn't look very normal. This is a great example. We're going to take a look. Let's see here.
Yeah, here, let me
I'm going to try and do this with the camera. The screen's backwards. I apologize, but you'll be able to get the idea. So the question is, if you were fuzzing SMS, for example, one, you wouldn't want to do this over the network because it would be expensive and it's just a bad idea in general. And two, you want to be able to rapidly test sending lots of messages with various permutations of data. So you can get an idea of, you'll hear a sound every message that's coming in. So those are all SMSs rapidly going through there. It's you win every time. And this makes it way easier. So literally we can send hundreds of thousands of messages through this extremely quickly. And it's pretty cool. So we'll just leave this running overnight, and you'll run a huge amount of test cases against this. It'll return if there's a problem, then we can go check and see if that problem is actually causing a vulnerability.
So right now we have 7 test suites defined. This one has about 299,000 test cases. We're about 200 in right now, so it's telling me I have about 900 minutes left. And I'll get to it a little bit later, but right now that's with a specific set of test cases, and if you wanted to leave this longer, the fuzzer can basically automatically go indefinitely and just get more and more in depth as you go.
Maybe we should stop it. Cool. So one of the other challenges with running this fuzzer, it's software-based, right? This is a piece of software. You could run it on a laptop or a desktop, but this is kind of a unique take that we've taken on it, is how do we massively parallelize fuzzing and do it across multiple protocols? So we actually built a distributed fuzzing cluster, if you will. It's in a TSA-approved case, so it can travel, although it's pretty unique traveling on a plane with this thing. It'll have, we've got 10 or 12 devices plugged into it now, Bluetooth, Wi-Fi interfaces, and then obviously a direct interface for other types of fuzzing. It's got 16 cores. It's massively concurrent. So essentially you can be attacking, 10, 20, 50 phones simultaneously across multiple protocols. This is a pretty unique innovation that we are leveraging internally, and it's amazing how much faster our testing goes doing this. So this is just an example of the extensibility of the framework, taking this protocol fuzzer and then extending it with some custom hardware, making it way more effective. And anybody could do, you could just use a laptop with a fuzzer, but even better, you can use some hardware for special purpose, high-end testing and run massively concurrent fuzzing simultaneously.
Mobile protocols are evil. Anyone who's ever read a OMA spec or 3GPP spec or ETSI or ITU, I am very sorry.
So we know you all have.
But basically, the issues are that they're very complicated. For a good reason. They're trying to put lots and lots of functionality, like literally a lot, into a very, very small space in terms of size. Bandwidth costs lots and lots of money on carrier networks, so the more things they can put in that bit mask, the better. So if you look at the WAP spec, for example, there's 40 pages of how WDP operates over various obscure bearers. It's pretty gnarly. The short of it is that a lot of the fuzzing tools that exist currently make it difficult to deal with nitty-gritty bit masks and then variable length fields that have the high bit set, and then when the high bit's not set, you stop, or things like that just make things just kind of nasty. Also, very well arrowed state diagrams. You have all these. If you look at the Bluetooth L2 cap connection diagram, if anyone's ever seen that, it's silly. There's just so many states, and if we want to fuzz all of that, there's no way we're going to be able to account for that manually. So being able to define all of these things programmatically and then have the fuzzer just kind of magically do everything for you, that's good. Oh, also intelligent defaults. So for example, if you have an integer, you want it to be able to fuzz that integer for length, and then you want to be able to override almost anything because there's an exception to almost every intelligent default you can possibly have. So an example of this is, let's take our default integer element. It has a name, or it's a type, so it's an int element, and it has a name. Things can reference that name, as you'll see later. The default is a 1 byte, and of course, endianness doesn't matter in 1 byte, but big endian. And so, without doing anything, it has a specific set of fuzz cases that will automatically be generated there. Let's imagine you said, well, actually, I have a 3 byte integer, and it's a little endian. Well, all you do is tell us that it is, in fact, 3 bytes and also little endian, and all the test cases will adapt to match that. Similar sorts of things for length elements, CRC elements, etc. Binary elements, string elements. You can pass in constraints and it'll tailor the test cases for you. Additionally, if you'd want, you can add specific test cases if you want to add your own. And then the other nice thing is that we have a set of opinions on what make good fuzz values. We've looked at some of what Sully's done, some of what some other fuzzers have done, and incorporated those. Anyone can define their own set of test cases. It uses a software principle called dry. So all you do is swap out one file, and all of the fuzzers will use the new default test cases. And you can add them, delete them, and hopefully we'll, from a research community, figure out what test cases actually are more likely to work, so we don't waste our time doing things that aren't. We talked about an override mechanism. So this is a little complicated example. This is specifically to build the lacing value in the OGG format. So what this does is a length element for the data element you see at the end. And so the length element will automatically grab the length of whatever protocol is attached later. So in this example, it's OGG, and then so Vorbis is the sub-protocol inside of that, but OGG doesn't know about that. So when Vorbis generates its data, it attaches to that data element, and this length element sees that and can encode this length field. And so you see it loops over the length, and just basically it's kind of an interesting protocol where it ends when something is less than 255. And so if you have, say, 256 length, you'll get an FF and a 1. Because it's less than 255, it's over. One note of caution here that you say, hey, this doesn't actually fuzz that lacing value. That's absolutely right. when you think about things that you're just building protocols based on their definition, it's like ridiculously easy to get caught in this trap of I'm going to implement the protocol, and you actually create a really good protocol implementation, but you don't actually fuzz it. And there are some commercial fuzzers out there that kind of err on that side. I won't name names, but it just be careful to make sure that you try to break everything. You know, the framework's not a substitute for creative thought. You know, we're all hackers. Think deviously. So one of the things that we wanted to introduce in this fuzzer is we've always saw this trade-off between coverage and time, right? If you have a billion test cases, it's going to take a really long time to run them. And you know, the two ways of thinking about the degrees of freedom here are how many values does a given element take? You know, so you have an integer, it takes 0, ff, 7f, 80. Does it take 1, 2, 3, 4, 5, 6, 7, 8, 9? You know, you could go ad nauseum there. The other degree of freedom is if you have, say, 10 elements, how do you choose which values of which element are combined to form a single test case? And this can get very, very complicated. Our goal is really to avoid combinatorial explosion. So, you know, in naive implementations, you know, if anyone's ever trying to write a fuzzer, you can get up to the 400 quadrillion test cases. You know, it will end sometime around the lifetime of the universe. So really, there's two methods that have been used before. One is the kind of the one at a time method, and generally it goes something like this. You start with a known good PDU, let's imagine like an HTTP post, and then you define it with a whole bunch of blocks, and then you take one block at a time and you manipulate that, and then you inject all of those packets. The good thing about it is it's really fast, and you can have an element take a whole bunch of different values, but it doesn't cover the bugs where you have, say, an HTTP post and a bad URL at the same time. And so that's the problem there. The other type of combination method it's called the Cartesian product method, and basically it says if you have 3 blocks, you iterate every single value of every single block in combination, and so you know you can quickly see how lots of large numbers multiplied together form a very, very large number. You know, it's almost silly. So the method we're introducing is basically kind of doing a hybrid between the two. We do progressively more combinations at the same time. And so what that means is you start with one at a time. So you fuzz one element at a time, then you take 2 elements and start fuzzing that, and then 3 elements and start fuzzing that. But usually when you get to 3 elements, you've spent so much time that it's not really worthwhile. The really good thing about this is that it allows you to test large protocol stacks. So where if there were so many combinations that you'd want to test, let's say you were testing L2CAP, RFCOM, and OBEX on top of that in the Bluetooth protocol stack. If you wanted to fuzz all those simultaneously, you'd be in the 10 quadrillion range. But with something like this, you can start with the most likely things to cause vulnerabilities, which is the 1 at a time, and then 2 at a time is slightly less likely to cause a vulnerability, having fuzzed 1, but still good. And so that lets you fuzz very broad and they get increasingly more depth. One of the reasons we built the fuzzing cluster is to allow us to do this really, really in-depth fuzzing. So here's a quick little example of what this is. It's, you can see it's not that complicated. The nice thing is the math can get pretty hairy inside, but it's all abstracted away, so you should never need to look at it. It just kind of works. Other important thing is that we're not just fuzzing the structure, we're fuzzing the state. And so what that means is that in different state transitions, or different states of a given protocol, you inject packets, and based on the state you're in, bad things can happen in different places. And this is also interesting to note because protocol implementations don't usually have a really complete state system. You'll find that if it's usually not really fully compliant, so this is pretty important in a fuzzing system like this. The other thing that plays into the state transition is, if you want to fuzz well, you need to make sure things go fast. And so what the framework does is that it automatically transitions to the right state. Let's imagine you're connected to Bluetooth and L2CAP and RFCOM. If you get some sort of thing that disconnects RFCOM, you don't want to have to disconnect back to the baseband and then go all the way up. That will cause your fuzzing to basically be like a factor of 10 slower than it needs to be. So the system basically is instrumented so that you can only go down to the level that you need to, and it'll pop right back up into the protocol you're trying to fuzz. So that really helps from a speed standpoint. We touched on this briefly. It's leaky, so the idea is that not everything is as well encapsulated as TCP/IP. How often have you seen a vulnerability in HTTP that resulted from some weird flags being set in TCP. It's not that common, but Bluetooth, for example, WAP especially, there's a lot of leakage between the layers, especially with authentication in Bluetooth. And so it gets really important to actually fuzz full stacks instead of just single protocols. And this goes back to why can we do this? Because the combinatorial system doesn't explode when we add lots and lots of fuzz elements into a given fuzz test case. Other thing that's kind of neat is that, so let's imagine you're building a fuzzer. When you have to do all these state transitions, it can get pretty hairy because you actually have to implement a lot of the protocol. And so, being lazy hackers that we are, we didn't want to rewrite all of these data structures. So we basically have a way that the data structure definition can be used not only to fuzz things, but also to read data in from a buffer and to write data out to a buffer. And so actually writing protocols once you've defined a fuzz test case is surprisingly easy. It makes life not too bad. So as John touched on earlier, we disclosed a iPhone vulnerability in Bluetooth around 1.0. We used it with an early version of this fuzzer that we're going to be releasing. And it's in the SDP protocol, which is basically a way to enumerate services on a device. You say, hey, what things does this device support over Bluetooth? And it says, hey, I support PIM push and human interface device spec and OBEX and this, that, or the other. The interesting thing is here that the SDP protocol has this concept of data elements, and it's kind of a type length value format, but it's kind of quirky. This vulnerability basically uses an unknown type that's basically one off from the maximum type in the specification with a valid length identifier and a valid length. And really this element data, we basically just see like a kernel protection fault at FFFFF. It's kind of lovely. And so this is one of the first kind of remotely exploitable iPhone bugs found, and it was a good example of how fuzzing these kind of mobile protocols can be pretty gnarly. And this did not require any sort of authentication. All you needed to know the MAC address, and then so people like Josh Wright and company are developing some new radio stuff with USRPs to basically pull MAC addresses out of the air. Also of note is that the iPhone Wi-Fi MAC address, I believe it's still one off from the Bluetooth MAC address. So it's not impossible to find. So we were happy. Apple was really great, and they we showed them, they were able to duplicate it, they fixed it, and like I said, 4 months is phenomenally fast. The other vulnerability that we disclosed to Microsoft last year is another WAP vulnerability. And it also, like the one we disclosed earlier, is a result from a security misconfiguration. In this case, there's this concept of a WAP provisioning document, which carriers can use to change settings on a device. And under normal circumstances, a carrier would use this to bootstrap your phone, maybe set up your proxies, set up your NAPDEFs, basically get your phone up and running. Under a lot of devices, what happens is that the security policies are set such that it does not require a trust relationship of the initiator. It accepts basically anything. The caveat here that makes this not as bad as it could be is that it requires something called a network pin, which is your IMEI, to be present in that message. So this is probably not something that's wormable, but you can imagine something there are, if you know where to look, USRP software that can pull stuff out of the GSM baseband, and the IMEI is sent over the clear in that. So that makes this a potentially bad issue especially for targeted attacks. You can imagine if you can reset somebody's proxy, you can basically snarf all of their web connections. We disclosed this, and the fix tool that we released also fixes this vulnerability.
So we talked about how we're auditing. Let's talk about actually attacking mobile devices.
So the mobile landscape is what we like to call the 1999 factor, which is probably a slight exaggeration. It's probably not quite as bad, but right now the state of mobile security is very similar to how it was back before everyone started caring about security on the desktop world, where no one had all these protections in place. There's many phones right now, or the operating systems running on them, are not using heap or stack memory permissions to keep them non-executable. Stack cookies are used on only a few different platforms. space layout randomization on the stack and the heap and library loading. Very few people are using any of that, or they're only picking one or two things to randomize. At this point, for a lot of developers in the mobile world, security is kind of an afterthought. They've never had to deal with it before. It's never been a problem. And it's only within the past year or two, or I guess the past couple of years, that they've really started to realize, like, hey, we need to start caring about this stuff. But things are starting to improve within the past year or two. I know the iPhone specifically, they originally, everything was running as root on that phone. There were no protections whatsoever. Now they have a segregated user account, the mobile user. They're actually implementing, they're not doing ASLR. They're doing actually very, very strict memory permissions on their heap and stack, where they're both non-executable. But if I recall, they go as far as to disallow any page from being writable and executable at the same time. You just cannot have that. Windows Mobile and Android recently, I believe as of 1.5, they have stack cookies now. The Windows Mobile stack cookie is only a 16-bit cookie though, so I can't imagine it would be too hard to brute force that. The iPhone and Windows Mobile both use signed code for all their applications. Windows Mobile will, I believe it'll allow unsigned code to run, but installation will give a prompt to the user.
Mm-hmm.
Right? But on the iPhone, at least on a stock iPhone, all code that's running on there needs to be signed. Android, they don't code sign their apps, but they do kind of use a known bad list, which we'll talk about that. So some of the specific platforms, we're just going to kind of paint a picture of what it looks like on there as far as their protections, what they have in place, and some of the security or problems that they have. With the iPhone specifically, a lot of people are unlocking them so they can use their phone on T-Mobile or other GSM carriers. Just recently they had problems with the push notification service, where everyone thought that it was a problem on Apple's side, but it turned out that it was actually a problem with all the people unlocking it. People were getting IM push notifications that were destined for other people, and just push notifications were going to incorrect people. And the push notification service is it's based on XMPP, which is used for Jabber. And then they use SSL certs to basically authenticate each individual user, and they use that those keys as basically your user ID to identify you, and that way they know who to send this push notification to. On these unlocked phones, since those I believe were generated during activation, they weren't getting those generated, and so they started copying the private key onto all these different ones and using the same private key that they were sharing. And a lot of people speculated they could use that for spam to be able to mass send out all these push notifications to lots of people all using the same private key. We also have the App Store on the iPhone. The App Store kind of enables a lot of, it's a centralized location for people to download applications, obviously. They released their SDK, which made it easy for a lot of novice programmers or people who had never programmed in their life to sit down and write cool applications for the iPhone that do a lot of cool things. All this is running as native code, and a lot of these developers have no clue about security or are even aware that these kind of problems exist. Luckily, all the apps aren't running as root anymore. But one of the problems that we have...
Except for the SMS parser.
Yes, the SMS parser is running as root. So one of the problems that makes it a lot easier to exploit the iPhone is that a lot of people are jailbreaking their phones. It was definitely a lot more common before the App Store came around. since the App Store has existed, I don't know if it's as common for people to do it, but it enables them to have access to applications that Apple denied from being in the App Store, or people who just don't want to deal with that to still have their code released. But it does turn off code signing on the iPhone so that any software can just execute on there, whether it be malicious or good. And it allows it a lot more leverage for exploiting stuff on there. On Android, basically everyone was talking about how it was all going to be done in Java and everything was going to be running in a VM, so it would all be sandboxed and a lot more secure. Well, everything is running in a sandbox on there in VMs as Dalvik bytecode, which is basically just they compile the Java language down to. I believe talking to Jesse Burns said that it was actually going to Java bytecode first, and then they had something that was translating it to Dalvik bytecode and combining everything to one giant class. But not everything on there is actually running as the Dalvik bytecode. The VM itself is all native code, and then they also allow JNI code, which is basically native extensions for C, or to be running on there, so that you can optimize stuff for speed to have it be a lot faster. This is only recently officially supported. Before that, everybody was kind of hacking together stuff out of the SDK, and basically the I don't even remember what it's called. The one for creating your own distribution of Android.
The full source, the fire hose.
Yes. People were kind of hacking that together to write JNIs to distribute with their applications in the Android market. And this was being allowed but wasn't officially supported until last month. Currently, the NDK, it doesn't really support any third-party libraries. It has support officially for libc, libm, the math library, and libz. But compiling your own third-party libraries is not really a problem. You can basically pull out stuff to do that with their NDK. And that kind of goes back to the same problem that we were talking about earlier of using these third-party libraries that contain vulnerabilities. And a lot of these users that are creating these applications aren't aware that these kind of problems exist. Also, we looked for vulnerabilities in the Dalvik VM itself, basically to try and be able to exploit it from within the application but down into native code. One of the vulnerabilities that we found was in the JDWP, which is debugging stuff for Java. In the DVM debug output array, which is basically used to output an array, there's an instance where it's all users supplied arguments of the length of the array, and internally I believe the code was trying to expand the buffer that the array would be copied into, but it had a lot of signed and unsigned problems where the expand buffer was treating it as a signed integer, and it would add it to the current length of the buffer and say, is this length bigger than our current length? Well, when you added that to it and it was a negative integer, it would say, no, it's not bigger than what we have, and return that back. But then the copy itself was treating it as an unsigned integer. This isn't really a problem in the real world because this is for debugging purposes. But a lot of dev phones are out there in the wild. People bought them. It was the first Android hardware released. And a lot of those dev phones have processes running with open JDWP ports listening. But like I said, it's not really a realistic vulnerability as well because it's an integer overflow that requires like 2 gigabytes of memory to be copied over.
The cool thing about the Android security model is that it assumes that if you're a given process, it doesn't use the JVM to enforce some sort of security sandbox. It uses the Unix process space, which we can assume is a lot better than the JVM at enforcing security. This vulnerability, if it were exploitable though, and because dev phones have open ports, would allow, say, anyone on your neighborhood Wi-Fi network to do something to you. And so that would violate the security model because you are not the user on the device, and so you're exploiting somebody else's address space.
Yes. And the Android also has an app store that has a lot of the exact same problems that we covered with the iPhone, with first-time programmers developing applications and having no knowledge that these kind of problems even exist, and also with there's no code signing on these, and anything is allowed in there, and anything that they decide is bad, they just kind of add that to a blacklist, and instead of allowing known good like Apple does. Kevin's going to talk about the
current versions of Windows Mobile are based on WinCE 5, and what that means is there's one giant 32-bit address space for all processes. There's a whole bunch of slots. Each process has a slot, and it does some kind of cool pointer mapping. So slot 0 maps to the current process that's actually running, the current context. And then if you hit something in slot 0, it'll actually be the same as if you physically if you physically access the correct slot. The weird thing here is that you can actually have threads that migrate between processes. It's kind of neat. The scary thing is, though, that if you are in a process that has access to other processes, you kind of lose this memory isolation. So, for example, the SMS parsing in Windows Mobile is done in something called device.exe, which is a kernel mode, or not really, it's a kernel mode privileged process. So if you exploit that, you can touch any memory anywhere. The Microsoft App Store is coming, so we can probably see a lot more third-party applications. So the security there is a concern, certainly. A lot of applications are going to be written in .NET, so that certainly helps things, potentially more secure than C and C++. But there's still a lot of Win32, MFC, ATL stuff floating around in Windows Mobile, so there's a lot of room for vulnerabilities there. Windows Mobile 7 is pretty neat. It's going to be based on the WinCE 6 core, which does actually have real process isolation, so that's awesome. In the past, we've disclosed a few vulnerabilities in Windows Mobile, some in Broadcom, where it was kind of interesting. We actually drove down to San Diego, went to Broadcom, and sat down next to their engineers and said, "Hey, here it is." And they said, "Oh yeah, I see it. Let's add a test case." Okay, fix. This is an example of just kind of one of those silly length field off by n overflows that cause stack corruption. It's just silly. Colin Muelliner, a few years back at DEF CON, talked about some MMS vulnerabilities on Windows Mobile, and there's been a recent Bluetooth directory traversal in HTC devices. Once again, these are problems because it's very hard to get a patch out. I guarantee there's a lot of people with our Bluetooth vulns still floating around and haven't updated to the latest firmware. Certainly for the HTC vuln, how many people who have HTC vulns actually go check the HTC website, figure out where the download section is because it's kind of hard to find, and then actually translate my AT&T 8925 to the HTC Kaiser, and basically nobody does. So it's, even though there's the patch available, nobody applies it. The patch really exists.
Was that a problem with just the driver, or was that was not in Windows Mobile itself?
Yeah, so this is an issue, right? Because a lot of we worked with a lot of the manufacturers, so the OS vendors and whatnot, and they do a really good job of securing their device. And the manufacturers typically do a pretty good job of securing their device. But a lot of times there's third-party ISV code floating in there, and it's kind of this this pass the ball, who's to blame, who fixes it, and that causes a lot of coordination headaches. And so it's certainly something we're going to be seeing a lot more of in the future.
So we talked about attacking, auditing. Let's talk a little bit about defending mobile devices. There's definitely not one silver bullet in defending mobile devices. There's a number of pieces in the puzzle, and I think it's going to take cooperation and contributions at every level for us really to make progress here. The first, software security. So any software developers, from the operating system vendors down to and especially independent developers, so just individuals like us, like anyone out in the audience writing applications, super important that you're aware of developing secure code and the best practices in doing so. That's going to be important because it's death by a thousand cuts, right? If there's lots of little problems because of software security issues, that's going to be a continued headache moving forward. Device security, actually securing the devices themselves. This is especially from the OEMs and operating system vendors, really important that they take into account testing and making sure that security is at the forefront of developing their devices. network security. So we saw a couple SMS-based issues. Networks, the operators rather, are going to be able to filter a lot of these attacks, which is great, but that's not a one-stop shop. It's important that even though they're able to filter something, that it's something that the device won't be impacted by. So I'd say they have to work in cooperation with each other, because as we've seen with mobile, it's never a perfect situation. There's always edge cases. There's always things that happen that cause mobile devices to act in ways you might not expect. So cooperation between device and network security is important. Then finally, end user security. So even if we write secure code, there's the device security, and the network operators are doing a great job at network security. End user security is really important, and a great example of this is, so on the iPhone, there's lots of vulnerabilities that get patched in every cycle with updates. They do a pretty decent job of staying on top of that, but if you're an end user who doesn't sync with iTunes often, and at night you just charge on the wall when you're sleeping, you may be 5 versions back or n versions back and completely vulnerable to 100 vulnerabilities. And that's a really big problem. They've done their part, you need to do yours, and it's important that you're aware of that, especially for anyone who's responsible for an enterprise deployment and you're introducing the iPhone or other mobile devices into your enterprise deployment. I don't think really people take into account patching and firmware and software being up to date on mobile devices nearly as much as they do on desktops. It's a big deal, and you have to do your part to make sure that you take the next step and that you are up to date with what all the people in the value chain have essentially provided for you. And then another is just these devices, they're computers, we take them with us everywhere, they're really easy to lose. I would say take the appropriate precautions to make sure that you lock them down, password protection, encryption if that's important to you, to make sure if the device falls into the wrong hands that you can deal with it. We've heard a lot of stories about people who lose their devices with remote wipe capabilities, but will wait 1 or 2 weeks because they really hope they find it. My advice is don't wait. If you actually think that it's gone and there's important data on there, kill the device immediately. You can replace the device, but the data falling into the wrong hands, that's something that you just don't want to deal with. So looking at software security, device security, network security, end user security, these are all pieces that I think we know enough about security today. We've had 10 plus years of experience with what's happened in the wired world on the desktop. There's so much to learn, but that we already have learned that we can apply to mobile and hopefully get ahead of a lot of these problems. So as an end user, what can you do as a takeaway? You can definitely take action to drastically improve your security. Like I said, ensure the latest firmware and software is on your device. If you have a device, I challenge you, just go check and see if you're up to the latest version of your firmware or different software pieces. You might be surprised. Enable only essential services and protocols, especially if you're going to be at DEF CON. I recommend turning basically everything off. Verify any and all software deployed. This doesn't matter as much for end users. I would say, especially for enterprises, there's this interesting phenomena of end user supplied devices that are introduced into the enterprise. So a user buys their own iPhone, but then connects to a corporate network, or just is given a certain device by their company. Making sure you understand what type of software is deployed on that is really important, especially in cases where you could download software through the internet, not through a controlled source. And there's positives and negatives to both. We won't get into that. I mean, I think it's pretty balanced, but understanding that there could be potentially malicious software that your users are inadvertently downloading, that's definitely a big problem. And then finally, just establish a system to monitor mobile vulnerability disclosure and information. Kevin talked a little bit about that. We've got a great tool that we've put in place that basically monitors all the different information sources of mobile security and specific mobile researchers into a Twitter feed and other social media feeds that enable us to aggregate what's happening there. And there's easy things you can do. Just keep up with the disclosures of the OS vendor that you're using as well. And staying on top of that is really going to help you. We're not seeing nearly as many vulnerabilities as we are in other places on mobile, but it's starting to pick up pretty quickly. So if you just put simple systems in place, you'll probably be able to keep up with it. So we definitely want to thank you all for talking to us. We want to thank MSRC, the BlackBerry security team, Google and Android and Apple. They've all been great in working with us, and hope to continue to work with everybody. A few references and reading materials for everybody. There's some papers that I definitely recommend you check out if you're interested in this, and if anybody has any questions, definitely let us know.
So quick, if you do anything and you work for a mobile handset company, please, we're going to be releasing the tool. It's going to be free and open source soon. use it, and if you can't use it, send me an email and say, hey Kevin, yeah, this sucks because of X, Y, or Z, and we promise to fix it, and we really just want people to help make phones more secure.